Welcome back, AP Physics 1 students. So you just saw the video of the demonstration with the magnet and the paper clips. By the way, that's a great one for you to try at home if you want to see that it actually works. It's not just a magic trick, it's real physics behind it. And so the question becomes, what makes a material magnetic? So you need this notes page in front of you. This also goes right along with the last activity in the electricity and magnetism activity, how the magnet was falling through the copper tube, which then had the charge moving through it and then allowed a magnetic field to be produced. But in class I would show you that if we did it through an insulating tube, it just wouldn't work. So the question is, why are some things magnetic, some things aren't? Copper itself is not magnetic, and yet it contains magnetic properties. What's going on here? So there are only 3 intrinsically magnetic elements, which means you can dig them up out of the earth. They will already have magnetic properties. In class I would ask you if you knew any of them. Maybe you do, maybe you don't, but let's just go ahead and write them down. They're going to be iron, nickel, and cobalt. Here are their chemical symbols, Fe and I and Co, iron, nickel, and cobalt. And so you can just dig them up out of the earth. They'll already be magnetic. So the question is, why are they magnetic and other things just aren't? To answer this, we will go back to our original discussion of the fundamentals of magnetism, where we said that if you take a bar magnet and break it into pieces, each piece will get its own north and south poles. We drew some pictures of that. We showed the broken magnets, and each piece got its own north and south poles, but I did say you can just keep going, keep breaking it smaller and smaller and smaller, and every shard that breaks off will still have its own north and south poles. It will still have a magnetic field all the way down to the atoms inside. The atoms inside these materials, iron, nickel, and cobalt, have magnetic properties. Remember, this is why we couldn't get down to the monopole. There's always north and south poles. The question is, what's going on? Well, let's draw a picture of, well, right here on your paper, some sort of solid material. Here, each circle here represents the nucleus of one of the atoms inside. Well, not all materials make this sort of cubic structure. We're just going to pretend it's some sort of crystal like this. We know all magnetic fields are produced by moving charges. So the question is, where are there moving charges inside the atom? Well, of course you know, it's the electrons, right? The electrons moving are tiny little bits of current, which means they create tiny little magnetic fields. So let's say this is some magnetic material, some non-magnetic material. We're looking at the electrons moving around inside. Let's say it's the aluminum of a paperclip. Paperclips themselves are not magnetic, and so they do these electrons moving around inside, and we're going to really simplify it. Let's say each atom only has one electron moving around, so we're going to draw some electron orbits. Let's say around this nucleus, the electron is moving around this way, and then around this one it's moving around this way, and this way, and this way, this way, this way, this way, this way. And so with some non-magnetic material like aluminum, these electron orbits are rather random, but each one does represent a tiny bit of current, which makes a tiny magnetic field. So if you use your right-hand rule shortcut, it will show that the magnetic field produced by this one will be pointing to the right. And if you just do it for all of them, you'll see the magnetic field is pointing perpendicular to the loop, following the right-hand rule. And since all the electron orbits are random, all these tiny magnetic fields are random as well. And so this one here will cancel this one, this will cancel that one, this will cancel that one, and overall the net magnetic field is 0. This is what it looks like inside some sort of non-magnetic material like aluminum. So what does it look like inside iron, nickel, or cobalt where it is magnetic? Well, if it's all about these electron orbits and here they're random, what does it look like here? Well, they're not quite so random. So maybe they're all oriented this general way. I just arbitrarily picked one direction, which means all the magnetic fields line up. And so instead of canceling each other out, they will support each other, they'll reinforce each other, making a net magnetic field pointing to the right. And this is what it looks like inside some sort of magnetic material. And so inside the aluminum, where it looks like this, when you put it near the strong magnet, it forces the electron orbits to sort of orient themselves along the same axis. So all the magnetic fields sort of support each other, they reinforce each other, they make a net magnetic field, but it doesn't like to be that. It'll hold on to this for some amount of time, which is why in the demonstration in the video, when she took the magnet away, the aluminum paperclip still retained the magnetic field. So they stayed like this for some amount of time, but not a very long amount of time. Little by little, they'll sort of click out of place and randomize themselves to form the picture on the left. And if you want to try this at home, you can sort of help it out by dropping the paperclips. When you drop the paperclips, it sort of shakes them up and re-randomizes them to this, and they lose their magnetic properties. Another way to view this is the concept of magnetic domains. You can sort of imagine in some sort of non-magnetic material that there are little sections of the material where the magnetic field points in different directions, in different sections, and so they'll cancel this one, this will cancel this one, they cancel each other out. But then when you have this external magnetic field, the domains are aligned with this external field. This magnetic field sort of forces all these tiny magnetic fields to align with it, which is why the materials inside the aluminum sort of pick up the magnetic field produced by the bar magnet. But again, it is a temporary situation for something that is not as susceptible. It doesn't want to stay magnetic for very long.